This is a continuation of that lecture. This is still lecture 6. So the way that is done is, or a way that is done, this is what is called the Diffie-Hellman message is the following. So there has to be some information that Alice and Bob have, and Eve has it too, but somehow they have to be able to send each other a message to transmit a key that even though Eve knows the basic information, she's not able to figure out what their keys are. So what is it? Public knowledge will be a prime P and an integer G. Which is, let's say, just for simplicity, a primitive root, mod P. So someone comes up with a prime P and an integer G. It could be Alice, it could be Bob, it could be the government that just announces here's a prime and here's a primitive root. So everyone knows P and G. And then this is what Alice does. Alice chooses her secret number A. So A is a number that's picked by Alice, and only A knows it. She's never going to transmit it. But what she does is, so A chooses her secret number A and computes the number capital A, which is congruent to G to the power A mod P. So she takes G, everyone knows the primitive root G, everyone knows the prime. Alice takes G, raises it to the power A, reduces that mod P, and that's the number she calls capital A. And Alice transmits the number A to Bob. And Eve, capital A. And Eve knows what it is. Eve sees every message. So Alice chooses a secret number A, computes this capital A, and sends A to Bob. Bob does something similar. Bob chooses his secret number B and computes what? He takes G, raises it to the power of little b, reduces it mod P, and calls that capital B, and sends B to Alice. So everyone knows capital A and everyone knows capital B, but no one knows little a or little b. All we know is if capital A is G raised to the little a, the secret number A is the logarithm of capital A to base G, and the secret number B is the logarithm of capital B to the base G. So you might say, well, if Eve knows capital A and G to find little a, Eve just has to calculate the logarithm of capital A to base G. Similarly, to find little b, which is Bob's secret number, Eve only has to calculate the discrete logarithm of capital B to base G. The problem is, for Eve, computing the discrete logarithm is hard. No one has an efficient algorithm to do it. If you pick a large prime P and a large primitive root G, any primitive root output, G, this is a problem that can be done in a finite amount of time on any computer, but the amount of time might be 100 million years. And it doesn't do you any good to say in 100 million years, I can decipher your message. So the crux of the Diffie-Hellman key exchange protocol is that computing the discrete logarithm of an integer, given the prime P and the primitive root G, is computationally too hard to solve in any reasonable amount of time. So even though Eve knows the prime P, the primitive root G, and these numbers capital A and capital B, she doesn't know the secret numbers A and B. And notice Alice knows her secret number A. Bob doesn't know the secret number A. Bob knows his secret number B. Alice doesn't know his secret number B, and she doesn't have to. So, but what is the key? There's supposed to be some number that Alice and Bob both have. Alice gets capital B from Bob. Bob gets capital A from Alice, but what is the key? Well, the key is the following. Again, here we have Alice. She sends a message A to Bob, which is based on her secret key, her secret number A. A is congruent to G to the A mod P. Bob has a secret number B. He computes capital B, which is G to the little b mod P, and sends B to Alice. And Alice does the following. Alice takes the number B and raises it to her secret number A mod P and calls that A prime. Bob, who got the number A from Alice, capital A, raises it to his secret number B and reduces it mod P, and we call that B prime. So Alex has capital A prime and Bob has capital B prime. And what can we say about these things? A prime is congruent to B to the A. B is G to the B raised to the A, which is G to the AB mod P. B prime is A to the B. What is A? Little g to the A to the B, which is G to the AB mod P. So A prime and B prime are both congruent to the same number, G to the AB mod P. So that means that A prime equals B prime. And this is the key. This is the key number. So Alice and Bob both have this number, it's the same number, A prime and B prime. They can use that as a key for their code. And Eve, who knows A and B, capital A and capital B, can't figure out what this is. Because the only way she can get A prime is if she knows the number, the secret number little a. And the only way she can get B prime is if she knows Bob's secret number little b, and she doesn't. So somehow, even though every message back and forth has been intercepted, and even though everybody in the world knows what the prime P is and the primitive root G is, Alice and Bob have managed to establish between them a secret key that they can use for their cryptographic schemes. And that is Diffie-Hellman. So let me just sketch an example, which is the example that's worked out in the book on page 69. And that's the following. You take the prime P equal 941, and it turns out that the number 627 is a primitive root. So for Alice, she chooses for her secret number little a equal 347. So her number, capital A, is G to the A, which is 627 to 347, reduced mod 941. You don't want to do this by hand, but a computer can do this almost instantly. And if you take 627 raised to the power of 347 and reduce it to 941, you get the number 390. So the number that Alice sends to Bob is 390. Let's say Bob chooses his secret number, little b, to be equal to 781. And then the number he's going to transmit is 627 to the power of 781, reduce mod 941. And that, as it turns out, is equal to 691. So Alice sends her number 390 to Bob. Bob sends his number 691 to Alice. And what is the key? Alice takes 691 and raises it to the 347th power. So this is exactly 627 to the, to the 781 times 347. And Bob takes 390 and raises it to the 781st power, which is 627 to the 347 times 781. Again, these are trivial on a computer to calculate. You just don't want to do it by hand. And each of these numbers, as it turns out, your computer does the calculation for you, is 470. Modulo the prime, 941. So Alice and Bob now both have the same number, 470, that is going to be the key that they use for their encryption. So this now gives them a key so they can securely transmit information to each other. And Eve, the interceptor of all their communications, has no idea that this 470 number is the key. That is the crux of the difficulty. That's it.